Good. Yeah, it would be fun if you were here yesterday.
Yeah,
it would be interesting things to say about it on the panel too.
Oh yeah, yeah. We could have dragged him down, made him work for a.
Yeah,
but,
it could be useful.
He maybe wouldn't have come back, right?
That's true.
Well, you'll have to pick on him today.
Oh, no. I've done neutrino math already, unfortunately.
Yeah, but there's other things.
Yeah, that's I'm Susie maybe.
Yeah. Is everybody here? Is it 2 o'clock?
It's very precise.
Should we tell jokes for a minute? Or?
Go ahead, tell jokes. I want to listen too.
Look, 3 physicists walking into a bar. Okay, so.
Okay, sure.
Okay, take it away.
Okay, so yesterday we sort of started by saying, we ended by saying we're going to talk a little bit about the chiral perturbation theory today. Okay, so again, this is according to Tom's word a very poetic description of it. It's not, but it's sort of trying to use this to set the language and some concept that you're going to be useful later. So what's the picture? Picture that we know that something happened at a scale called the lambda QCD. Let me just call it 1 GeV. Okay, this is a huge can of worm. What is lambda QCD? But let's just call it a GeV. We know the couplings become strong. Things start to form bound state and so on. Okay. Naively, you will say that's it. It's beyond our current computational technology, at least the pencil paper computational technology. There you can do this on lattice and so on. Okay, but it turns out that there are things you can do more. Okay, even pencil paper. It's the first indication that you may be able to do something more is the observation that there is a light mesons. Okay, so such as pions. Okay, so pion it's about 100 MeV mass. Okay, so and you see, now this looks like a nice setup that I may be able to do something perturbative about this state. Okay, so I have a cutoff, but I have something that at energy relevant energy much lower than the cutoff. Okay, well, not that much lower, but at least 1 order magnitude. Okay, so which you will see it's actually true. Okay, so you see that the one of the small expansion parameter you wanted at energy scale relative similar to pion, the small expansion parameter you could find is this. Okay, which is true. Okay, you will be able to you will be able to do computations with that small expansion parameter. Okay, so now let's just go ahead and start. So the first puzzle I think you wanted to ask yourself is that why is this much lighter than that? Okay, sounds a little bit strange, right? Because proton and the neutrons, other bound states are right around the QCD scale, and this is much lighter than that. Okay, so right now, of course, I think most of you know the answer. Most of you know the answer, and but I think it's still in the original idea. I think it's very impressive. Is that since it's much smaller than QCD scale, maybe its mass is we should be approximately thinking about its mass is 0. Okay, so but we know the series that can give you 0 mass scalars. Okay, what are these series? So why is axion mass 0? Shift symmetry. So these are Ghostos. Okay, so then the conjecture is these are actually following from some spontaneous symmetry breaking, and these are the Ghostones. Okay, breaking what kind of symmetry? You wanted to take the inspiration from the UV theory of QCD. Okay, because the global symmetry structure there, and starting with the global symmetry structure there. So here there is a bit of choice. Okay, so depends on what do you think. So obviously we're only going to talk about the light quarks, because heavy quarks like charm and bottom, especially top quark, the mass is way above QCD scale. So at the level we're talking about, you should more or less integrate them out. Okay, at least well, let's integrate all three of them out. Okay, so they are not there. So the quarks that is in your theory is up, down, and strange. Okay, and even this, you may have second thoughts about that. Okay, because this is actually 100 MeV-ish mass. So, but let's just do it nevertheless. Okay, and you can if you don't want to think about that, we can just deal with these two flavors too. You know, the story is completely the same. Okay, so now the QCD Lagrangian for these is just it's just this, right? It's a vector-like and so on. Okay. Therefore, the global symmetry of this Lagrangian. What is the global symmetry of this Lagrangian? Yeah, SU3 left cross SU3 left, the right. So SU3 left cross SU3 right. Notice that this is different from the SU3 we wrote yesterday. Okay. So these are, yeah. Well, yesterday the SU3 is a UCT, right? This is different. This is just these three things. Okay. So yeah, under which Q goes to ULQ under the left rotation, and the Q goes to URQ under the right rotation. Okay, and then you guess that this is a QQ bar is a good Lorentz invariant operator, and looks like this is something that should get a VEV. Okay. And I think this is called a vector-like confinement. So then with this getting VEV, this breaks this symmetry. Okay? Because left and right cannot rotate independently. This breaks this symmetry to its diagonal subgroup. Okay? Maybe we can call this vector if you want. Okay? Is this okay? So that's the symmetry breaking pattern. Now, this is spontaneous symmetry breaking. Therefore, there will be Ghostones. How many Ghostones are there? 8, because there are 8 broken generators. So 8 Nambu Ghostone bosons. Okay, and let's just call them pi i's. Okay. So in reality, they have slightly different names. Okay. Just okay. Now, so how do we describe Ghostone bosons? Huh? Nonlinear sigma model. So, okay, but we don't need to go there. There's also nonlinear sigma model with CCWZ formalism and so on. Okay, so, but we don't actually need to go to that deep. Okay, but it's basically just exponentiate the Ghostone fields. Divided by a scale which I call the f pi. Okay, so the convenience of doing this the convenience of doing it like this is that the global symmetries still acting on these fields linearly, acting on sigma linearly, even though, so the global symmetries acting on pi's, they look like shift symmetries. One of you already said. Okay, that's why basically this has no mass terms. Okay? And this is not very convenient. Okay, but acting on this is still linearly. So sigma goes to UL dagger. Okay, and this so-called chiral symmetry breaking is the spontaneous symmetry breaking in terms of sigma field is nothing but just this guy has a VAV, okay, which is 1. Is this okay? So this guy has a VAV 1 that breaks these two rotation into their diagonal. Okay, only the diagonal rotation keeps this VAV invariant. Is that okay? Okay. All right. So now we can write the Lagrangians in terms of sigma. So we start with the lowest dimension Lagrangian, right? So and also the kinetic term with 2 derivatives and lowest dimension. Okay, so f pi squared trace okay, so this is the lowest dimensional Lagrangian. Okay, so and you can expand this out in terms of pion. And this is partial pi, partial first term. And this is actually infinite, has infinite number of terms. Okay? All of them have 2 derivatives, but the later terms has more pi's in it. Okay? So I have pi square trace commutator square. Okay. Sorry, I have adopted a notation that but I don't want to always write this out, right? So I say pi is just this stuff. Okay. Right. So that's why they don't commute. Okay. They are generated. Of course, if there's only one Ghosto and so on, obviously this term doesn't exist. And yeah. Okay, so this is the theory of massless pions. Okay, not just pions, but there are 8 mesons, 8 light mesons. At this level, they are all massless. Okay. Okay. So now, but the chiral symmetry breaking, the chiral symmetry is not a exact symmetry. Okay, there are also other things that breaks chiral symmetry. Okay, in addition to the spontaneous symmetry breaking, there are explicit symmetry. Right? Explicit chiral symmetry breaking. Okay. Yeah.
So maybe before it goes to breaking, so can you clarify the meaning of a phi? So it's phi on decay concept, but as you write it there, it's like a normalization concept, but it's not like it's a vacuum.
It's related to this vacuum valve.
So the actual.
I'm actually, yeah, I may get this wrong, but this is roughly speaking like this. Okay. At that level, it's just a normalization. Then you can build the full Carroll Lagrangian. You see that that one has the interpretation of pi on decay constant. Okay.
But physically, just the actual number comes from what without QQ bars.
You can understand that way too. Yes. Sure. Yeah. But
I'm sorry. How was that? This expectation value that pi squared consists of? So you have explicit sigma 1 that seems like.
no, sigma is not literally QQ bar. That's not necessarily QQ bar.
Yeah,
right.
but you have to expand it out.
I expand. Oh, sorry.
It just looks weird. This sigma has all the pi's in it.
Sigma has all the pi's in it. We're talking about two different series. So that is the quark description, and it's not very useful at the low energies. Okay, you should probably stop thinking about sigma as a QQ bar. Okay, you can try to do a matching with the quark description and that it all works out. But I don't want to do that. Okay. Yeah. So already at this level, at this level, you can even just say that, okay, this looks like I don't think you are making a huge mistake to just say this is a lambda QCD cube. Okay. Then to do a more detailed matching between this series and that series, and this is slightly more accurate, I think. Yeah.
But it's somewhat confusing to me. So I was always confused by this point. Why is it so confusing to scale phi? Phi looks like this normalization.
At this level, I forget about that. I just tell you there is a theory. There's SU3 cross SU3 go down to SU3. I ask you to write the Lagrangian for the Ghostones. It's this one. I haven't even at this level. I haven't even identified what F pi is. Okay. And then you wanted to compare this. Right. Then I haven't even interpreted what F pi is yet. Okay. So if you want, I don't have to call it F pi. Let's call it F, and later on you will see this is So I'm not sure I will go there actually, but anyway, let's talk about explicit symmetry breakings. The chiral symmetry is not a good symmetry. Okay, there are explicit symmetry breaking parameters. Okay. In particular, it's broken by quark mass. These quarks are not massless. Okay, it's broken by quark mass. Right. So let me write it as in the spirit of SU3. Let's all write it in the 3x3 matrix form. Okay, these are the three masses. Okay, that I have to include. None of them are equal. Okay, if they are equal, there's a larger symmetry, but at this level, it's broken, completely broken chiral symmetry. And okay. And but as I said, that I'm allowed to think about these are small parameters. Okay, basically because these things are smaller than the scales I'm talking about. Okay, so the QCD is a GeV, and these are to a couple MeV. This is about 100 MeV. So if you really don't like, we can do a two-flavor chiral perturbation series. That's enough to describe the pions already. Okay, so okay, and then we should think about this as a sporions that breaks the symmetry, right? So in the spirit of sporion analysis, I can imagine these sporions also transform under chiral symmetry. Okay, so just in order to write a Lagrangian, okay, in order to write the coupling between these sporions and the pions in a covariant way. Okay. And that then I can start to write the explicit breaking terms, which, let me write it. Okay, you can verify that if I think both of them, this term is invariant under the transformation law of this and that. Okay, and okay. Now you will be even unhappier. Now I have a new parameter mu. Okay, but this is all this can all be fixed by compare with experiment. Okay, so it's just fixed by these are phenomenological parameters at this moment. Okay, now if I expand this out in terms of pions, this is 2 mu trace m pi squared. Okay, so give you pion mass. Okay, which is not surprising because I explicitly broken the symmetry. The Ghosto should not be massless anymore. Okay, so this give you this is to the second order pi. Okay, so okay. In particular, okay, now let's write some formulas. M pi 0 square is mu mu plus md. M pi plus minus square is called. I haven't explained what the why is a different charge yet, but I'll do it soon. This is m pi 0 square, degenerate of m pi with m pi 0 square at this level. Okay, but experimentally, you can also calculate that there is a correction. Okay, and this correction is calculable. And there's mk0 square, which is mu times md and ms. So this is the mass of k-on. And mk plus minus square is mu over 3 and mu plus md plus ms. Okay, so these are kind of predictions you can get just from this simple analysis. No, that's wrong. That is completely wrong. This is mk0 square plus delta m square. Okay, and there is eta square, which is the formula I just wrote. Okay. Okay. All right. So now you say, so what? So you still have one free parameter, right? You still have free parameters here. So even if you know the quark mass, okay, you still have the free parameter. But again, the non-trivial thing is that I just fix one, then I know all of them.
It's like 7, not 8.
Yeah. Yeah. So sorry. It's eta prime is U1 eta. That's the thing that we haven't talked about. Yeah. Am I missing someone? Yeah. So there. Yeah. Right. So there's a k long and a k short. Yeah. And sorry. So now you can predict all of them. Turn this thing around. You can also say that I measured all these mass, right? It's supposed to. So these are the things certainly have been observed first, right? So I can turn this around. I can solve for these masses, okay? And you can calculate the ratios of these quark masses at least. So ignore delta m squared for the moment. Okay, so you can calculate this, and they actually agree with the experiment to a few percent. Okay, so this works pretty well, despite of some initial doubt about whether this works or not. Okay. And now let's come to this delta m squared. Okay, delta m squared obviously is the difference between the charge and the neutral ones. This coming from the fact that the QCD is not the only interaction in town at this energy scale. Okay, there's also QED. Okay, these quarks carry different charges. Okay, so the QED coupling itself breaks chiral symmetry as well. The gauging of QED already breaks chiral symmetry because the quark doesn't have the same charge. Okay, so imagine that again, in the same spirit of 3 by 3 matrix, so I can write this. Okay, so this also breaks the SU3 rotations. And you can also calculate, just use the Spurian analysis, the splitting that this caused on the of this. So, but you can already, you can more or less guess. Well, in modulo some details, you can more or less guess what this is. Okay, let's just guess. Okay, it's some QED coupling. Right, so it's proportional to E squared. So it's not directly contributes to the mass. Okay, it's just after all, this just appears in the gauge interactions of the. It's not directly a mass term, but it's just pi plus minus. It's this kind of couple corrections. Pi. It's this kind of corrections. Therefore, I include a loop factor here. Okay, it's quadratically divergent. Okay, this contribution is quadratically divergent, but this is a series with a finite cutoff. The cutoff is lambda QCD. Okay, the series is valid up to lambda QCD. Above that is a different series. Okay. So, roughly speaking. Okay, and this is roughly correct. Okay, so in detail, this is a cutoff. This is a cutoff, not exact lambda QCD. It's by another resonance called rho, and that's then if you want, you can improve that calculation. But it works. Okay. So all of these, I think, has analogies in the later in particular, for example, in composite Higgs models, where we talk about. Okay, so it's almost identical ideas. Okay. Right. Okay. So these are the mass spectrums. You can also this is more than chiral perturbation theory can do more than that. Okay, you can also calculate the pion scatterings with for example with chiral perturbation theory. Okay. So let's just do it quickly. So suppose I wanted to calculate pi scatterings, which we actually do it in the lab. We can do it. Okay. And at energy around m pi. Okay, not much higher m pi, and I can use this theory, and you see that already this term give you a contribution. There are 4 pi's in it. Okay, give you a contribution. So the amplitude of this is f pi squared, right? And derivative square. Okay, but in Fourier space, it's just energy square. Okay, so I imagine that I have a center of energy E and so on. Okay, and that's it. Okay, so of course you can refine this this calculation. Okay, there are additional terms you can add to this Lagrangian. There are e to the fourth to f pi e over f pi to the fourth corrections too, if you want to make a more detailed prediction of this coupling. But the behavior, the leading order behavior is this. Okay. Now, already you see that this series. Suppose I don't know about the quark theory. Okay, I just somehow guessed because I see a number of light pions. I guessed this low energy. I guess I guess this is the symmetry breaking pattern, and these are the Ghostones, and so on. I do experiment. I'm pretty happy that I can actually predict certain result based on that Lagrangian. But already at this level, you know this cannot be the whole story. Okay. Because this amplitude will become strong when energy is higher. Okay, so you can maybe you can think about this as using this as a definition of 4 pion coupling. So 4 pion will become strongly coupled when the energy is bigger than phi. Okay, so now when do you call strong coupling? That's a matter of taste, but. Let me call it strongly coupled if this becomes 4 pi square. That's just my choice. You can make your choice too. So the simple motivation is that if you view this as a coupling, then if coupling is this strong, all the loops are equally important. Okay, all the loops are equal at least. Well, and so that you see that this, you see that then you will say that if this equal to this series should break down. Okay, I should hit a cutoff. This series should transit into some other different series. Okay, because this series becomes very strongly coupled. Okay, so it should become something else, and this gives you the cutoff of the series should be 4 pi times f, roughly speaking. Okay, so even so this again, this is something else we can emphasize is that from effective field theory point of view, the effective field theory tell you where the series breaks down, and there's a cutoff, and this is this case too. Of course, in this case, we know this. We know what this is lambda QCD exactly, and this formula actually works pretty well, and in this case, and the new theory is a theory of gluon quarks. Is this okay? This is very good. Okay, so let's come to our next topic, which is electroweak symmetry breaking. So just put this in the back of your mind for the moment. Where should I do this? Okay, do I need to wash the board already? Let's wash the board. Yeah. Okay, so maybe let me make a few remarks first. Just wait for the board to dry. So, I think historically, well, as far as I can tell, the symmetry, the fact that the gauge bosons somehow have mass has been a quite confusing subject. Okay, so the earlier law is that the gauge symmetry prevent gauge bosons to have a mass. Okay, and you know, then I think the first non-abelian gauge theory, at least attempt, was trying to come up with some theory that can describe a weak interaction and so on, but immediately was thought it was not really viable because they predict the massless gauge bosons and so on. Okay, and yeah, so. But of course, now this is all very understood in terms of Higgs mechanism. So I think you have all seen Higgs mechanism before, but let me do it in a way, probably, you know, again, slightly different perspective. Which one is dry enough that I can write on? Maybe I will just start from way back. Ah, good. I'll just start here. So, okay. The first thing you want to the first attempt to say there's a massive gauge boson is just to say I will add a mass term. Okay. And I think that this was dismissed, you know, people, this is not gauge invariant. Okay, this is bad. This is basically the idea, the foundations of saying that gauge symmetry forbids a mass term. Right? But of course, that's not completely correct, and it's actually fine. You can actually do this. Okay. To see this, you know, I think you know you can actually do this already. You know, even if after you've done all the Higgs and so on and so forth, you can always go to unitary gauge. Unitary gauge, it looks like this. Okay, and so it must be fine. It's just a gauge choice. Okay, but the physics is more transparent if I consider a slightly different gauge. Okay, so I will instead of this, I will write this term as with some suggestive notations. Okay, I'll write it like this. Okay, and these two are completely equivalent. Okay, if you want, they just differ by a gauge transformation. They are completely equivalent with each other. The physics are identical. Okay, but already from this term, you see that this is a fully gauge invariant. Okay, so the gauge invariance is guaranteed. Okay. By the way, I'm not going to carry around all these non-abelian indices, but some non-abelian is understood. Okay, just it's same story for the U1. Okay. Okay. Now instead of A transform, but also pi shift. Okay, this is this series is gauge invariant under the following transformation. The only novelty here is that pi transform nonlinearly. So gauge symmetry is realized on pi in a nonlinear way. Okay. Nothing wrong with this. Okay. So gauge symmetry does not the so-called gauge symmetry does not prevent you from writing down a mass term. Okay. But what does this do is make manifest that the inclusion of mass term means that you don't just have this. Okay, you are propagating one more degree of freedom. Okay, so you are propagating in one more degree freedom, which is this term is just the kinetic term for that extra degree of freedom. Okay, that's okay. All right. And of course, this is again totally expected because we know massive gauge boson has 3 polarizations. So in addition to the 2 transverse mode, you have to have something more. Okay. Of course, you all know that this is the Eaton Ghosto and so on. Okay. Okay. So if I just take a weak interaction, and do this, okay, that's fine. Right. And this is the Higgs mechanism, okay, if you want to call it. This is the Higgs mechanism. Right. And this is what we do, well, mostly what we do before 2012. That's all we need to do. Explains all the experimental data before 2012, just with this. Okay. However, we know this series is incomplete, cannot be extrapolated to arbitrary high scales. Okay. So, to do that, let's just write a few more steps. Okay. So this is a Ghosto. We just went over how to do Ghosto properly, right? So let me just repeat, more or less repeat what I just said, which is I can package the Ghosto into a nonlinear sigma model field. Okay. The normalization constant is V, okay. And the Lagrangian of that is just the V square trace d sigma square. Okay, and okay, that's it. That's what I have. Okay, so So because I'm propagating the Ghosto, there has to be a piece of Lagrangian look like this. Okay. So it turns out that I can also, just very similar to do pi scatterings in QCD, I can also do Ghosto scatterings in the standard model. Okay. The way to do this is to do WW scattering. Let me draw a blob instead of draw all the diagrams. Okay, but let's just draw all the W scattering. In particular, I'm going to do this scattering at a very high energy. Okay. Again, this is where we know, at least in our pion series, we know that we see the series should break down at high energy. So I also wanted to do this at high energy when E is much greater than the mass of the W boson. Just like there, I'm doing the energy is greater than the mass of the pion. And the polarization vector for the W, the longitudinal polarization. The longitudinal polarization vector is proportional to P mu over M. Okay, so at very high energies, it's longitudinal dominated. Okay, so at very high energy, I can imagine this is all just longitudinal scatterings. And the longitudinal part is exactly the Ghosto. Okay, so if I do, again, then I do WW scattering at very high energies, I'm essentially doing pion Ghosto scattering. Okay. The formal statement of what I just said is called the Ghosto equivalence theorem. Okay, the statement is you can take any W's and get very high energy. You can replace that with the Ghosto, and you get the same result. Okay. But okay, so since it's just pion scatterings, then we can just derive the result from this Lagrangian. instead of going through the standard model gauge interactions and so on. Okay, so this is proportional to the amplitude of this is proportional to the E square over V square. Again, almost identical to the story I just erased. Okay, so and we know that this theory cannot be the theory, the final theory. At higher energy, it will break down. The energy it will break down or cut off is again 4 pi times V. Okay. And by the way, in general, I should write this as a covariant derivative and so on. Okay. From this, you can also see that the MWs and Zs are on the order of GV square. Okay. So this also gives you MWZ. Just you can also make a prediction for that. And this is about the 200 GeV. Okay. For our purpose, let's just call it 100 GeV. And we know that 1 TeV. So even though the theory I just add a mass term can explain everything what I do, I know that once around the TeV, the theory will break down. Okay. In other words, something needs to happen either at a TeV or before TeV. Before TeV is okay too. Okay, it just never hit the strong coupling point. Something happened before that. That's fine too. Okay. So sometimes this is called the no-lose theorem. Okay, because sometimes if you want to spend a lot of money build a collider, you wanted to make sure you can discover something. Sometimes, not always the good motivation, but if that is your motivation, there's a no-lose theorem. Okay, before 2012. Okay, in the late 90s and in the 90s, and you do have that no-lose theorem. Something needs to happen before that. Okay. And of course, we don't need a new collider to go there. LHC is capable of probing a TeV scale. So, so yeah, there are many ways. So by
before we could actually measure physics, how do we know that?
We don't know. We could. Yeah, that's literally what I just about to say. There are many ways that this can be rescued. This problem can be solved. Okay. So by the way, this business of solving this problem, I don't know. It's not a very good name. It's called the unitarization of WW scattering amplitude. Okay. This is just okay. The idea is that when you go to high energy, amplitude become very large value to unitarity. So something has to happen before it to unitarize the amplitude. Okay. And there are many ways to unitarize the amplitude. Okay.
So you imply that you need Higgs.
I'm about to say it. Yeah. But it's important to have this perspective. Higgs is just one of the ways. Okay. So, in fact, this is what we're going to talk about, since that is already been discovered. The simplest new physics, the simplest way to unitarize the amplitude is to add a singlet scalar. Okay, is to add a singular scalar, not arbitrarily, but add a singular scalar to this combination. So this is e to the I pi over v. But extend this into added to in a very particular way. Okay. Just add it in a very particular way. Okay. Notice that I'm calling this a singlet, and that this is a singlet. Okay. This does not transform under SU2 rotation. Okay, obviously you know this is the Higgs boson. Okay, this is the Higgs boson we discovered. Okay, this is a singlet. First thing I would say, this is a singlet. Okay, and it does not transform in SU2. Second thing I would say, it has nothing to do with mass generation. Okay, so it's not the particle that generates a mass for you. Okay, W bosons don't propagate in the vacuum, scatter with Higgs bosons to get mass. Okay, it's because the vacuum has spontaneous symmetry breaking. Yeah. So this is just a way to unitorize that amplitude. That's the definition of Higgs boson, if you want. Okay, so of course, now with this, in addition to the original diagram, we know it's divergent, and you have additional diagrams you can draw involving Higgs bosons. Okay, you can draw this, for example, and you can draw a few more. Okay, and you see that once you add this all up, and the energy diverging behavior cancels. Okay. Of course, you know ahead of time also, this will have to happen. Okay. The reason that this will happen, you know this will have to cancel, is that this is just one way to write that field. The way that the e to the minus e to the I pi and times that's just one way of writing that Higgs field. Okay. Field theory, I can do arbitrary field redefinitions. One useful field redefinition is to recognize that I can package that 4 degree of freedom. There are 4 degree of freedom there. Okay, so 3 goldstones and one. I can package that into this. It's just a field redefinition away. Okay. And this is a doublet, complex doublet. Okay. And with doublet, I can write gauge interactions like this. Okay. And in this theory, obviously, there's nothing. Okay. There's no energy growing behavior. Okay. There's no 1 over mass scale in this theory. Okay. So therefore you know that theory cannot have the physics shouldn't change depending on which field definition you use. Okay. So that has to be fine. Okay. And what is the Higgs mass? Hmm? 125 GeV. Okay. And notice that this happens much earlier than it's needed. The unitarization of amplitude happens much earlier than it needed. Okay, that's fine. Okay, nothing wrong with that. And so on. Again, let me emphasize again. So before 2012, we don't know whether this is a picture or not. This is the simplest picture. There are other pictures. There are many other ways I can imagine, but they're all more complicated by some measure. Okay, by the measure there are more fields I have to talk about, and they involve strong interaction. They involve other things. Okay. Right. Imagine there's no guarantee whatever you unitarized amplitude will be a weakly coupled theory with a single resonance. Right. There can be a QTD-like theory, for example. Okay. Yeah.
So besides mass, what properties of that?
Yeah, let's talk about that later. Yeah, it's a scalar. It's not spin 2, and it decays to diphotons, so it cannot be fermion. It can only be scalar or spin 2, and it's not a spin 2 because they measure it. Of course, none of us believe it's a spin 2, but it's more or less CP even. Even though in this one is obviously CP even, so it's more or less CP even, and then there are all kinds of other measurements that you can do, and we will probably have a chance to talk about it at some point. Okay. Okay, so let's go on. Okay, now we have our, and this is basically our electroweak symmetry breaking, the so-called standard model way of doing electroweak symmetry breaking. Now let's again consider additional symmetries in this Lagrangian, okay, which also have interesting implications. In particular, let's talk about the custodial symmetry. Custodial SU2, sometimes called the C. The C is not color. It's called the custodial symmetry. Okay, let me explain what that is. To do that, it's useful to think yet another representation of another way of writing down the Higgs field. Okay, slightly more cumbersome, but it's useful just to think about that representation. Is to write the Higgs field as the following. This is basically the anti-symmetric tensor. This is in SU2 wise. For SU2 wise, this is a doublet. This is also a doublet. Okay, because SU2 is pseudo real, and they have different hypercharge, but they have different U1 charge. But that's not what we're going to focus on. Okay, so I will write it like this. Okay, and I can write this as in terms of component. This looks like the zero neutral component of the Higgs field. On the diagonal looks like this. Okay. This is a little redundant, but as you see, writing this way, it will make certain symmetry much easier to visualize. Okay. All right. Now, in this way, I will start with my Lagrangian. Okay, you can verify. I can actually write that Lagrangian in terms of d mu phi dagger d mu phi. Okay, trace where d mu phi is okay. I already grouped the Pauli matrices and the W into a three-dimensional vector. Phi. So I have two gauge couplings. Okay. This is SU2. This is a U1 hypercharge. Okay, I can write it like that. You should check it. Okay, so I think take you 1 minute in Mathematica to check it. And notice that there is the curious fact that this is a sigma 3 here. This is just coming from the fact that the hypercharge for Higgs and Higgs dagger is different. Okay, that's just this is embodying that fact, and this is the usual SU2 interaction. Okay. All right. So let's think about symmetries. Okay, let's think about symmetries. And first, obviously, the whole thing is a SU2L invariant. Okay, the SU2L is act on this as this on the left. Okay, so this is a 2x2 matrix. So it's important whether it's on the left or on the right. So this is on the left. And in this case, you can verify this is under this transformation, this covariant derivative goes to UL Okay. So with well, it's understood that I have to do a corresponding rotation on the W's as well. Okay, this goes to UL. Okay. So this is just a global version of the SU2 gauge invariance, if you want, and under which W transform like a triplet. This is basically saying W transform like a triplet. Okay, it's SO3 rotation on W. W is the fundamental of that SO3. Okay, so that's certainly a symmetry. Now, on the other hand, okay, let me for the moment consider a limit where G prime goes to 0. I'm going to turn off hypercharge coupling for the moment. Okay? If you want a motivation, it's smaller than SU2 gauge coupling. Okay? So I would like to identify the symmetries with the large terms in Lagrangian and treat the small terms as spurions. Okay? So this is what I'm doing. And with this goes to 0, I'm just ignoring the last term. And there is also a SU2R symmetry. Okay, on this, which act on this on the right. Okay, SU2R rotation. Okay. That basically, this is the reason I wanted to write Higgs field in this silly form. Because I can talk about this more easily. Okay, and in this limit, d mu phi goes to d mu phi ur deck. Okay, because there's nothing, right? You're just acting on this on phi. Notice with this term it's not, because if you act it from this side, then you have to go through sigma 3 first. Sigma 3 is not invariant. Okay. Yeah, that's precisely the reason that this is a spurious term. Okay, so okay, all right. Now, of course, electroweak symmetry is broken. So, electroweak symmetry breaking. What does it mean? It means that the phi has a VAV. Okay, like this. And turning on this VAV means that these two are not separate rotations. They are not separate symmetries anymore. But a diagonal subgroup of these two are still the symmetry. Okay? So this takes SU2L times SU2R to its diagonal, which is SU2C. So this is a diagonal. It's called a custodial SU2. Okay, SU2 custodial. And under custodial SU2, W is still a triplet under custodial SU2. Okay, because W is a triplet under SU2L. Okay, anytime I rotate, I have to go through W. Okay. All right. So, all right. Okay. Now, already at this level, you can draw some conclusions from the symmetry breaking here, because there is a symmetry under which W is a triplet. Okay. You conclude that their mass are the same. Okay? The 3 W bosons has the same mass. Okay. Of course, this is broken by the fact there is a finite G prime. Okay? So this is only broken at this level, meaning at the tree level, by G prime. Okay? By turning on a finite G prime. Okay? And which is true. I mean, you can obviously verify this by just start with this Lagrangian and work it out. Okay? But it's, as I said, it's always useful to identify what's the symmetry behind it, so that in order to write new things, you don't destroy this relation. Okay, that's what's important. So, I don't know whether you have seen the mass matrix of W's or not, but let me just write it in the mass matrix of W's. There are 4 gauge bosons. Their mass matrix is G square G square. So I have a V square here. G square. Yeah, maybe a half. Maybe I'm missing a half. Okay, so, and that's it without a G prime. Okay, these 3 has the same mass. Without a G prime, obviously this doesn't couple. Okay, so then there is a GG prime. GG prime. Okay, so custodial symmetry basically dictates the form of this matrix. Okay. All right. Very good. Yeah. So let me just write the actual formula of W and Z's. And sometimes it's people define a parameter called rho, just to capture the fact that at the standard model at this level is 1. Okay, this parameter is 1. Sorry, this cosine theta angle is just a rotation among this submatrix here. So cosine theta W square is this is called a weak mixing angle, sometimes called a Weinberg angle. Okay, this is not clear what the W stands for. Anyway, so, but this is the tree level relation, okay? And let's see. And this means that since standard model is weakly coupled, experimentally you should observe this parameter, this ratio to be 1 with small corrections. Okay, so let's just let me also mention already in the standard model there are some small corrections to this at 1 loop level. First, I haven't talked about the Yukawa couplings yet. Okay, haven't talked about quark mass yet. Okay, so let's talk about the Yukawa couplings. Okay, it turns out the Yukawa coupling can also be written with this guy. Okay, instead of H. You're probably more used to seeing it with the doublet, but I can also write Yukawa couplings with this field. And it looks like this. I'm writing the top Yukawa couplings because they are the largest. Okay. So top and bottom Yukawa couplings because BL, and this is the value of phi. So let me just put V here. Okay, and TR, BR. No. Okay. If that's all there is, top and bottom quark will have the same mass. Okay. That's what the Yukawa coupling do. Okay. So you have to insert something like this here. Okay. But this means that SU2 rotation is not a symmetry of this term. Okay. So since y top is not the same as y bottom, SU2C not a symmetry. Okay. And so there, in the standard model, there's already, in addition to the hypercharge G prime, there's additional spurions to break custodial SU2. It looks like this. You say, oh, top Yukawa coupling is pretty big, but it's still a small correction because this is not directly a gauge boson mass. It enters gauge boson mass at one loop. Okay, so let's just draw those diagrams. Perhaps. Good. Okay. So there are diagrams you can draw. Obviously, this has to involve top and bottoms. For W mass, there is a top, bottom. For Z, top part. For example, there are diagrams like this. Okay. These diagrams give you corrections to the relation of WZ mass that I just write from the tree level. Basically because the top quark mass breaks custodial symmetry. Okay. So in terms of the rho parameter, this gives you a correction to the rho parameter. Okay. Since these are top quark mass, top quark Yukawa coupling, connected, related, you know it has to proportional to top Yukawa coupling. Okay. Since it's correction to mass, so it's V squared, so it's YT M top squared. Okay. This is proportional to M top squared. So I'm going to just give you a very rough formula. I have a better formula on the notes. Okay. So it's something like this. Okay. And then since this number is dimensionless, okay, the way I define it is just the ratio of two masses, so it's dimensionless. So something else has to make up the dimension. So it's okay. It's roughly something like this. Okay. And in the standard model, this is about 1%. The actual calculation is this is about 1%, and the data has been very well tested too. Okay. And so far. But you know, so this is actually dependent on the top mass. Okay, This is another way of saying is the WZ mass ratio depends on top mass. I have only talked about the tree level effect of hypercharge, right? So just in the mass mixing, it breaks custodial SU2, but hypercharge can also give you one loop contributions, okay, to the WZ mass. Let me just. So that goes like the Higgs. This is the leading contribution. Okay. Higgs. Okay, this is the hypercharge. You can understand. You can if you want, you can imagine this is the hypercharge gauge boson. Okay. And this gives you also a delta rho. Again, it's G prime square because it's hypercharge. And right. some factor, log, well, loop factor first of all, and some other numerical factor, then mh squared mw squared. Okay? So this contribution is also important in the standard model, but it depends on the log of mh squared. Okay? The difference here and there is the mass of Higgs itself is not a sporion. Okay? That's why it's in the log. Okay? It's just the scale that you have to, there's mass is a little heavier than the W boson, the Z mass. Okay? So there's a log. Okay? So, all right. So, of course, both of these effects has been very well tested. So, in my note, I included a figure, and these kind of figures usually goes like you can do MW in the plane of, because MW is the firstly measured and the M top. Oh, first of all, it's just based on the measurement of MW and MZ. You can already try to make a guess of M top. Okay, just based on that formula, that give you some range already. Okay, and so in this range, I think, okay, it's usually something like this. So this is the experimental error bar on MW, and this is experimental error bar on M top, and you can try to, if you fix these two, then the ratio in principle depends on M Higgs. Okay, that ratio in principle depends on M Higgs, logarithmically. Okay, not very sensitive, but logarithmically. So you can have contours like M Higgs. Okay, different M Higgs. Okay, this is the last thing I'm going to say. I need 1 more minute, then yeah. So this is the reason that even before the discovery of Higgs, you can hear things that we sort of guessed what the Higgs mass is. Not very well because it's logarithmic dependence. But even before discovery of Higgs, the precision measurement of WZ mass pinned the Higgs mass below 200 GeV, roughly speaking. So 1 more minute, okay, just 1 more minute. Because this is really just the same topic, okay? There's also additional contributions that for new from operators you can write down that breaks the custodial SU2. Okay, you can write it in different ways. You can write it, for example, in terms of the sigma field. This will be because it's at this level it doesn't really have to do with the Higgs boson, so you can just write it with this. And imagine you plug in the valve for sigma field later, and it's custodial breaking because the sigma 3 here. Okay, or you can, if you want, you can write it in terms of the Higgs doublet, and that looks like this. Okay, and the test that we have run more or less says that M needs to be greater than 3 TeV. Okay, so anything you write that violate the custodial, when you integrate those things out, you will generate these operators, and those things has to be heavier than 3 TeV. Okay, so I think this is actually finished what I wanted to say about the standard model. Okay, next time we'll go on to be on standard model. Okay.
I just wanted to say that plot, maybe it's a little misleading because it makes it look like the error is small.
Oh, the different scale. Yeah, very different axes. Yeah, that's true. Yes.
Really, MW is measured to better than a part in 1,000.
Yeah, it's per mule level. Yeah.
MT is measured to.
Yeah. So I should say that the MZ, both MZ and W, and are down to per mule level. Okay, from E plus E minus lab measurements and so on, and a temperature measurement. And yeah, MT, as Len said, the error is about the GeV. So, yeah.
How did you measure
Yeah, so it's basically coming from something like this. Because the dependence on MT is much stronger than the dependence on M Higgs. Because that's a logarithmic dependence, and this is quadratic. Right. Top quark with 3 TeV. Then, okay, you can try to balance these two too. Okay, let's not play that game. Okay, so then you have to go way out on M Higgs and try to balance these two.
Can I maybe just ask one more?
Yeah.
So what happens if I add ortho?
Yeah, triplet web in general breaks custodial SU2. That's why if you add any triplet, it's the size of its web has to be very small. I don't remember, like MEV or something, right? That has to be very small. And the doublet, you can always, it applies to any doublet you want. Yeah. Yes, I should also say that. Okay.
Okay, so take a break.
Yeah. Huh? So usually these days, what the heck I'm doing?